Okay, so I went ahead and taken a PSC motor right here, permanent split capacitor motor, split phase, and I've ohmed out common to run, common to start, and I found out that run has 9 ohms, start has 30, run is less than start, and I've went ahead and wired this motor. Now, this particular job might be the most important job that you're going to see me demonstrate in this class for a service technician. We've already learned in theory that if we let a motor run away with itself, induction, the induced voltage goes way up, right? We're going to see that right here. This motor is unloaded. I have a watt meter, a true power meter, that's about a $5,000 meter, a little bit more potent than what your meter is, and I'm able to check volts going to the motor, real volts between common and run, and amps simultaneously together, and be able to get the true power that this motor is using. Now remember, power is watts, okay? So we have a 100-watt light bulb, you can relate to that. We can actually see how much wattage this motor is consuming, right? But we can also see how much it's consuming in the form of induction and how much is true power. Now what I'm going to do first is I want to show you here in watts, power. I want to show you something else pretty cool first. So I have it on volts. We're measuring volts right now of right here, common and run, and it's a 122 volt motor or 120 volt motor. And so common to run, how many volts? 122, right? 122. Now, what I'm going to do is I'm going to take the voltmeter and I'm going to check the voltage between run and start, which is called high induced voltage. I'm measuring all of the induced voltage of the run winding and the start winding. Okay, so I'm changing this between run and start, true high induced voltage. How many volts is coming out of the wall? 120 volts. Come and measure this. So this 120 volt motor right now, between run and start, is actually producing how many? 406 volts. 406 volts. Now, watch what happens as I add a load. Somebody hold this up so everybody else can see it. Y'all may move in here. It's okay. Smith, hold this right here for me. Watch the voltage. Actually, I can do this a little easier. Okay, looking at that top number there, can you see that? 390, 400 volts. Now, as I add a load to this motor, watch what happens to high induced voltage. What's happening to the voltage as I add a load? Talk. Goes down. Induction goes down the more load, right? Why? Because the motor's slowing down. The faster the motor spins, the more induction, the more magnetic field. Now watch this power factor right here. Power factor is the relationship. Power factor, PF, is the relationship between, let me get back over here, common, checking volts right now, common and run. This thing is only operating at 42% efficient. And what that means is that most 60% of the energy that we're buying, 60% of the energy is going into this motor in the form of heat. Why? Because it's running away with itself. High induced voltage, right? Now watch what happens to the power factor. It's at 0.43 right now, 40% power factor. Watch what happens as I add a load to the motor. What's the power factor doing? Talk to me. I can't see it.
It's going down.
Power factor
Goes down.
should go up.
Oh, yep, it's going up now.
Should go way up, like 80, 90%.
It's around 78.
Now watch this, I'm gonna hold on to the motor. What does it do?
81.
Really high. Why? Because right now it's pretty much a resistive load. Now it's back to an inductive load. So load on the motor causes the induced voltage to go down, right? But causes power factor to what? Go up. What burns up capacitors in the field? That right there. See that a while ago? Let's go back to that. 400 volts, 405 volts is what's going to this little run capacitor right now. That run capacitor is only rated at 370 volts. There's 400 volts going to it. How long is it going to last?
Not very.
Not very long. Now, if I put a load on the compressor or put a load on the motor, it's good. Okay?